So this is Euler's method, chapter 8, I believe section 1. So what is going on? We have a curve right here. This happens to be an e to the x curve. And in calculus AB, you learn a tangent line approximation. So at this point of tangency here, you draw the line. And as you can see, if you wanted the value of the e to the x curve, or in this case t, at 1, if you found the y value on this red line, it's kind of close to the actual value on the e to the x. And if you found it at like 0.8 or 0.6, it's really close. But the problem with the tangent line, look at 2. E squared, the value, if you found the value of this red line, it's not even close to the actual value here. So that's when we use Euler's method. So Euler's method, we do multiple tangent lines. So you have your original, but you're going to stop, and let me jump this to 2. Whoa, that's not 2. Let me see if I can get this to 2. It's very sensitive. I think it's better if I just type in a 2. Okay, so here is the idea. When we have an approximation for, what, 2.9-ish around here, okay? Now, you saw with the tangent line, we were way off, not even close, right? So now if we do 2, we stop halfway because there's 2 steps, 2 segments. And so you cut your distance in half, and you stop here. At this point, you do a new tangent line. This is your starting point, but you find the slope of the curve at that point, and you plug it in, and you get a second line, and it kind of follows the curve. Now, as you can see, as we increase, let me go to 3. Now we do 3. And as you can see for 3, it's even better because now you break this into 3 sections. So after the first section, you do a new tangent to this curve and it curves up towards it. At this point, you do a new tangent and it curves up towards it. And we're just going to keep increasing the number of segments. Okay, so let's go up to 4. And look, it's even better because now we break this into 4. We stop here, make a new tangent line, stop here, make a new tangent, stop here, make a new tangent line. So I'm just going to keep increasing the number. And I think you'll see, let's go to 5. It gets better and better because the more segments you have, the more it follows the curve. And as I increase the number, let me do this one more time. As I increase the number of steps, you'll see quickly that the more steps you have, it's going to follow the curve, and the approximation becomes really, really, really close. Now, in this class and on the AP test, we're probably, at most, we're going to do 4. But look at that, right there, that's 16. If you do 16 steps, a lot of work, but you're really close. And man, if I go up to 400 steps, that's almost spot on. So that's the idea of Euler's method. Now that you get the idea of how Euler's works, let's show you how you would do it. So you're given a starting point always. So we're going to call our starting point x1, y1. And so our original starting point would be x1, y1. Well, you're going to have to figure out delta x. And you're familiar with that. You take the distance you're traveling and divide by the number of times that you're doing this. In this case, we have 4 times. So we call this starting point A and end point B. So if we're going to go, this is actually 3 segments, so let me do 3 on this one. So in this case, N is the number of times you're going to apply Eulers, I guess you can call that. It's probably a better word for that. But you're going to do, 3 steps, number of steps, that's what they call it. So I'm going to write down number of steps. And in this case, we have 3 steps. You can see 1, 2, 3. So you're going to take the whole distance from here to here, divided by n, and that's going to be your delta x. So every delta x is going to be the same. That's pretty easy. Whatever you find, it's b minus a over n, whatever that number is. And we'll do an example. And it repeats over and over. So here's the deal. Let me take a look at one of these triangles. Let me draw one, and then we will break it down. So here is a triangle, and I'll fix, whoa, that's not a triangle. I'll draw a general triangle and then shrink it down to fit. Okay, let me make this correct. So I'm going to place this over my original and make it match. Pretty good there, eh? Pretty close. Pretty close. So that's my triangle. So as you see this, you should make the connection with this triangle here. Okay? So in this triangle, I claim the bottom piece is delta x, right? The distance from here to here is our delta x that we calculated. Oops, not that one, this one. And each time we move over the same delta x. So in this one, this would also be delta x. And this one, this would be also delta x. Well, we need to calculate delta y. So I'm going to call this delta x1. No, they're all the same, so I don't have to name them different. But the amount of delta y are going to vary. So if I have my original spots, and I know delta x and delta y, I can find my new x and y coordinate. So this one here would be like x2, y2. This one here would be my x3, y3. And this is my final, would be x4, y4. So if I did a straight line, tangent line, that would be, ooh, I didn't want to do that. If I did a straight line, just a single tangent line, that would be my approximation. This is more accurate to the actual value here. And the more you do, the better you're going to get. And the shorter the distance, the better you're going to get. So hopefully you can see that. So the idea, if I can calculate this delta y1, I would know where the new spot is. Because I start at x and move over delta x. That's easy. I can find x2, which would be here. And then to find my new y, my y2, I take my original y and add my delta y. So look at this triangle. And the question is now going to be, what is the slope of this line? And since it's a tangent line approximation, the slope is going to be the derivative at that point, right? So here is the kicker. Here is where all the fireworks fly. The slope of that line is rise over run, delta y over delta x. So we can find the slope of this line by getting the derivative. That's what we do here. We find the derivative, and that's the slope of that line. We know delta x because we calculated delta x. And so we're going to multiply both sides by delta y, or excuse me, delta x. Let me scoot this up. And here's the whole crux of Eulers. Multiply both sides by delta x. And what do you get? Now we have delta y is going to be the slope, but what is the slope again? The slope is the derivative. I'll write it down first. M delta x. But the slope is the derivative at that point times delta x. So we can find delta y by having the derivative, multiplying it by delta x. So once we find the derivative, multiply by delta x, we will get a delta y. Okay? So that is what's happening. So by multiplying, we will calculate a delta y1. So my new x2 here, I take my original x and I add my delta x, which I have here. And my new y, I take my original y, my y value here, and add the delta y. I'm going to add that. Well, as you can see now, we have a new x and a new y. We repeat this process and we get the next one. Repeat the process and we get the next one. So that is the idea behind Eulers. And I'm going to do one example for you with hard numbers, and hopefully this will all make sense to you. So we are given a differential equation for the derivative. We're given a starting point. So we know we start at 0, 1, our original point. Looks like we're doing 4 steps and we're approximating at 1. So we're going from 0 to 1. So our question mark is 1 comma what? What's the y coordinate there? Approximating using Eulers. Okay? And so now we can find delta x. It's b minus a. Whoops. So we're going from 0 to 1. So the distance is 1. We're covering 4 steps. So it's going to be 1/4. Now we know our delta x's are all 1/4. Okay? So we're looking good so far. Now, let's go through the process. Now, I can actually find all the x's because 0, I move over 1/4. This will be 1/4. I add 1/4 again. I'm going to be at 1/2. I add a fourth again. I'm going to be at 3/4. Add a fourth again. I'm going to be at 1. So that's where we want to end up. So we want the approximate y based on this method. So how do we do this? We need the derivative. So we need the derivative at our original point. What's our original point? 0, 1. So we want the derivative at 0, 1. How do we get that? Man, I should do this below so I have lots of room. So I'm just going to plug it into this derivative formula, 2x minus y. So it's going to be 2 times 0 minus y, which is 1, which is negative 1. Bammo. That's the derivative, dy dx at 0, 1, so I put negative 1. And then we calculated delta y is the derivative times delta x. So this will be negative 1/4. So we started at 0. Oh, no, excuse me. We started at 1. Our delta y, we went down 1/4. So our new y is going to be 3/4. Now we go through this process again. I need to find the derivative at the point xy equals, look, our new point, 1/4, 3/4. 1/4, 3/4. And do I have room to do this? The same formula, 2x minus y. So 2x, 2 times 1/4 minus 3/4, which will get us 1/2. I'll do 1/4, 2/4. 2/4 minus 3/4. Oops. That's negative 1/4. Is that right? I was so sloppy. Let me do that over again. Do it all over again. So this will be 2/4 minus 3/4, which is negative 1/4. So dy dx is going to be negative 1/4. Ooh, we're going to get some ugly numbers here. So delta y is the slope times the change in x to get change in y. That's going to be negative 1/16. So this is 12/16 minus 1/16. 11/16 is the new point there. Now we have to find our slope again. Dy dx at the new point. Our new point is 1/2, 11/16 at x, y, equals 1/2, 11/16. This is 2 times 1/2, right? 2 times x, yes, times or minus y, which is 11/16. That's going to be 1 minus 11/16. That's going to be 16/16 minus 11 is 5/16. So that's going to be dy dx. It's going to be 5/16 To get my delta y, I multiply these two. Wow. 5/64. So my new y, I take this one and add this one. So this is 44/64 plus 5/64 is positive this time, right? Yeah. So 44 plus 5, that's going to be 49/64. Usually they don't have ugly numbers like this, so bear with me. I just made this problem up randomly, and it's not so pretty. All right, so our xy now is our new xy, which is 49/64 and 1/4. Wow. Yeah. Equals 49/64 and 1/4. I'm running out of room. I'll put it down here. So it's going to be 2 times 49/64 minus 1, or plus 1/4, right? It's plus. Oh no, is it minus or plus? It's minus. I've been minusing. Okay, I thought I messed up previously. Hopefully I haven't made a mistake previously, but I think this will give you the general picture of what's happening. This will be 49/32 minus, to make this over 32, be 8/32, right? And 49 minus 8 be 41/32. So that's going to be my, my dy dx, 41/32. Multiply that, delta x, by the slope. It's going to be 41/32, 64, 128. Okay, we can do this. So we started at this y, and we increased by that much. This is actually, what, 98? 128? 98 plus 41? 98. Hey Siri, what's 98 plus 41?
98 plus 41 is 139.
139, 128. So, now my final step was here. So my approximation is 1 comma 139, 128. And so, approximate y of 1. Y at 1 is approximately 139, 128. That is the process of Eulers. That was kind of ugly numbers, and there's a high probability I made a mistake somewhere here with all these fractions and doing work in my head. But again, I think you get the process, and that's the end of this video.